Hello, my name is David Lee Jr., and this is my presentation for Lab 1 of Physics 2. Just to introduce you to the purpose of the experiment, we are looking to observe the interaction of charged pieces of tape to estimate the amount and charge of electrons transferred. Some fundamental concepts we'll be using include Newton's second law and Coulomb's law, but mainly for this experiment we'll be looking at the force of gravity and the force of electricity. Some assumptions we'll make is assuming each piece of tape had not only equal charges but equal distribution, particularly when you look at the point charge model, using the approximate size of the atoms to calculate ratio of electrons per atom on tape, and ignoring air resistance. I found two different charges for the tape depending on the method used at 1.72391 e to the negative 8, and then coulombs, and then 3.209511 e to the negative 8. Some initial conditions for the experiment. The length of tape I used was 0.19 meters, the mass is 0.19 grams, and the distance between the two pieces was 0.038 meters. For the procedure, you're going to really just need tape, any surface that's flat, and then you can use a ruler or a tape measure, and then you also need two pillars, basically two things that you can suspend the tape between. You have to stick the tape down, rip off another piece of tape, test for the charges, and then there are these different scenarios where you'll be holding it under suspended tape, and then you'll need to measure it with a ruler. Some observations, when looking at the charged tape in the hand, it would be attracted to the hand. When the two tapes were up against each other, they would repulse. When the tape was up against a neutrally charged object, such as a cup, it would attract. And then when it was up against a negatively charged pen, charged by rubbing it against my hair, the tape would also be attracted to the pen. So thus, the tape is positively charged. So from the data, again, the mass is 0.0019 kilograms, the length is 0.19 meters, the width is 0.019 meters, and the distance is 0.038. So first, I found the gravitational force, which is just mass times acceleration, and that it was 0.0019 newtons downwards. The electric force magnitude was 0.0019 newtons upwards because it is suspended. The charge on the tape, we know that there's zero acceleration, and like we illustrated above, the force of gravity must equal the force of electricity. So you just rearrange the equation for the force of electricity, and you find that the charge is equal to 1.7450 times 10 to the negative 8 coulombs. Some errors in here may be not accounted for air resistance, like we mentioned before, as well as maybe the tape losing charges when being handled in incorrect measurements. And as always, the system was the tapes, the surface, and the two pillars, and the surroundings were everything else. Some calculations also from that initial experiment. The number of electrons on tape B is equal to the charge that we found divided by the charge on one electron, and that was 1.091 times 10 to the 11th electrons. And then we also calculated the number of atoms, or I calculated the number of atoms on tape B, which is the area of tape divided by the area of atom. So the length of atom was given in the experiment, and the length of my tape was 0.19 meters, the width was 0.019 meters, so the area was 3.61 times 10 to the negative 3 meters squared, and that gave a total number of atoms as 3.61 times 10 to the 17th. Then I found the ratio of electrons to atoms, which you basically just divide the atoms by the number of electrons, and you get 3.3089 times 10 to the 6 atoms for every electron. And for the Glowscript code model, this is the code that I use. You can see I calculated the gravitational force, the electrical force. Those are the constants that I inputted. And you can see there's a slight difference from the sort of manually calculated version. But the force and the electric force seem to be pretty consistent with the manually calculated force. Here's the code for the line charge. This is treating the tape as a line of charges as opposed to a singular point charge. And those are different scales I use. So here the green arrows represent the electric force. The red is tape 1, which is suspended over the top. Blue is tape 2. The gray arrow on top is the electric force, and the yellow arrow on the bottom is the gravitational force. And you can see they're somewhat equal. So what was the magnitude of the charge of one piece of tape as calculated by your first computational model, where each tape is a single point charge? It was 1.723918 to the negative 8. And what was the magnitude as calculated by the second option? And it was slightly different at 3.209511 to the negative 8. And that was found using trial and error. So some things that may have happened was, we assume the charge is constant over time. That's not necessarily accurate. The tapes, we also assume the tapes have identical properties, and that meaning size, charge, and also that the tape is at static equilibrium, and the system is not impacted by its surroundings other than the two tapes. So what if electrons were positive and protons were negative? What would change about the observations you made with your tapes and other charged objects? I mean, really nothing. Electrons and protons aren't really tied to the name necessarily. Like, it's still positive or negative ions, so whether they were called two different things didn't really matter. It would still have the same result. And these two models are different because the line charge accounts for the charge being distributed along the length of the tape as opposed to being concentrated at one point, which definitely means the line charge model is more accurate. So overall, the choice of models can lead to vastly different results, as we saw that there's a big difference between the two different models. Electric forces can negate gravity, which is pretty cool to think about, and also objects can be charged very easily.